So my name is Tanmay, and I am an assistant professor here at the Learning Sciences and Assessment Department. Today I'm going to be talking about teaching AI for education based on my computer science and learning sciences background and some experience with curating AI for education curricula in Europe and Asia over the past 5 years. From a learning sciences lens, I'm interested in how we can enculturate our students into the interdisciplinary world of AI for education. Now, in an attempt to tackle this very ambitious question, I'm going to use a rather simple framing through which we can hopefully view the various forms that teaching AI for education can take. The first lens is that of learning about AI for education, which is really about talking to our students about the relevant methods and applications of AI. The second lens is that of learning with AI for education, which refers to using the current generation of AI system, their strengths and flaws, to improve our teaching and learning. The third and final lens is that of preparing for AI for education, which is a more prospective lens to envision the kind of AI systems we would like to design in the future, something that is lacking today. All right, so let's start with the first lens on learning about AI for education. Now, this strand of my work focuses on providing inquiry-driven learning experiences so that students can probe into the black box of AI algorithms. And of course, the goal is to promote AI literacy. If we look at the current landscape of AI for education, it often falls short in educating our teachers and school leaders on what this black box of AI is. So our conjecture is that if educators have the opportunity to observe, experiment, and play with this black box, tinker with this black box, that can actually help them in getting an overall understanding of what AI is and how it works, what its limitations are. So that's precisely the goal of this first strand of work, which is learning about AI for education. Here, we introduce a simulation-focused approach to teaching a very fundamental algorithm of neural networks to teachers and school leaders. Now, this simulation is newly designed, and it has a couple of different ways in which we allow for building. So on the top interface, you can actually see how participants can construct their own neural network for an educational problem that is very relevant to Singaporean context. Who needs help at school? So what we do is we design a data set of 200 students closely mimicking the Singaporean school context with very detailed data points and have students construct their own network to predict who needs help at school, right? So on the top, you see a network that was drawn by one of our participants. The interface also allows you to probe the confusion matrix to try and understand, what are correct predictions, what are incorrect predictions, where do the incorrect predictions stem from? And actually, you can even drill down to individual student report cards to see where the model flagged students as needing help or not needing help and diagnose possible causes. In terms of machine learning, this allows educators to actually do some kind of error analysis. And what we encourage them to do is go back to the network, try to reconstruct it, adjust the nodes, adjust the weights, for instance, adjust biases, and then rerun the model. And this is an iterative process, right? Now, something that we are continuously trying to do as we're trying to iterate on this idea is to have an ethics-focused version of this neural network simulation. So very simply, we want our educators to get a sense of ethical issues which are not very far away from the technological foundations. So here in the interface, we provide options for educators to actually split the confusion matrix. In this case, by protected attributes like gender or SES or ethnicity, In this case, it's by household income. And this is a very good way to initiate discussions about ethical issues like bias and fairness. Now, this is all built into the simulation. So in this case, one can compare, for instance, the left matrix, which is students who come from lower income households, and the right matrix, which is students that come from higher income households. And one can compare, for instance, the false positive ratio in how the system is making inequitable predictions across these groups, right? And that's a very good way to understand issues of bias. One can also look at the false negatives, which is actually a rather serious problem, right? Because we miss students who actually need help. So in this case, again, we have curated the data set deliberately so that students can see these kinds of discrepancies and probe through and try to understand what causes these kind of issues of bias and fairness, right? So there's no direct teaching here. We have designed these affordances in the simulation for students to probe and think through these issues of bias and fairness, right? All right, so the simulation sounds cool, but I think the big question is it effective? So I'm going to show you some results from very early trials of this simulation with 24 school teachers and 23 school leaders who come to us for our courses. We found that compared to school leaders, teachers found the simulation more usable. Now, usability is assessed via questions that you see or items that you see on the slide. So things like the interface design was easy to navigate, the visual design was good, things like that. Usability, a very HCI perspective. Compared to school leaders, teachers also thought that they learned more, so that their perception of learning effectiveness was also higher than school leaders. So again, learning effectiveness would be related to questions like, I think that I learned the foundations of neural network. Questions like that, perception questions. Now comes the interesting part. Actual learning with pre-post test. You see the trends flipped. Actually, school leaders improved. Now both teachers and school leaders improved from pre to post, but school leaders actually improved greater, as you can see from this cohency or effect size of 0.4, as opposed to teachers, who also improved, but with a smaller effect size, right? So these results actually highlight a clear discrepancy between perception and performance, right? And this is actually backed up by learning sciences work on desirable difficulties, for instance. So for teachers, probably the simulation presented an easy to use interface, right? And that resulted in high usability ratings. Their interaction with the simulation was not that messy. It was less effortful. But for the school leaders who rated the simulation lower on usability and learning effectiveness, actually engaged in a more effortful learning experience. So actually they did more work in a way to figure out how neural networks work. And that may have actually led to higher learning. So what's the takeaway from this first very quick sort of snapshot of work on learning about AI Ed? Intuitive web-based simulations grounded in locally relevant data contexts can make the black box of AI algorithms accessible and authentic to folks without a technical background. And the second message, I think, is equally important, where if we have our educators grappling with interfaces that are obviously not perfect, so they're less than perfectly intuitive, they can still lead to perceptions of high fluency, right? Or low fluency, but can still lead to perceptions of higher learning, right? So fluency is not the same as learning. And actually, these simulations are a good way to test this sort of discrepancy between performance and learning, as we found out from this initial pilot study. Today, I think with GPT or Claude, or pick your favorite tool, it's actually possible to create these kind of artifacts very quickly, right? Now here we went beyond that. But again, this is a low-hanging fruit that we can tap on, right, in terms of learning about AI for education. All right, so let's change gears a little bit and talk about teaching AI for education from the lens of learning with AI. So I'm going to show you one example of our empirical efforts in this particular strand. Now, when students have to learn with AI, I have a rather radical proposal. I think we don't need a perfect, all-knowing AI. So the question to ask is, what if intentionally flawed, even biased AI is the secret to helping us think critically or helping us to collaborate better? So we usually, from a computer science lens, we actually spend a lot of time, right, trying to get the bias out of AI. But actually, I think that's a great instructional opportunity, Leave that for the computer scientists. I think for educators, that's a good instructional opportunity to tap on these flaws of AI in a way. So again, in some recent empirical work that we've done here, we have used biased human-AI collaboration as preparation for human-human collaboration. So this is a pedagogical sequence that brings together human-AI with human-human collaboration, acknowledging that both kinds of interactions have their own strengths. So very simply put, in this pedagogical sequence, we program or prompt different chatbots to actually keep arguing relentlessly from one perspective, from a skewed perspective, right? So, just imagine a bot that is a technical proponent of AI ed, a bot that is a corporate proponent. So its arguments are actually slightly different from the first one. And then you have a bot which is an ethical skeptic of AI. Now imagine this for your own subject, right? I think it's pretty easy to imagine various biased perspectives in the areas that you're teaching. Participants talk with only one of these three bots, and then they take a stab at defending the bot's perspectives. Now this is an important part of reflection in this pedagogical sequence, because when you defend someone's perspectives, you get into their argumentation, even if it's flawed or biased. And that, again, involves critical thinking, a lot of critical thinking. I know this may sound like going, just like in the reverse, right? But actually, one can use this kind of a structure to manufacture high-quality debate before students go into collaborating with their human peers, right? So the learning sciences idea is designed cognitive conflict. This can then be followed by human-human collaboration, where everybody who has spoken to one of these three bots are put together to share their perspectives and argue on the issue of learning that they're trying to work with. So in the human-human collaboration phase, the debate that happens is actually grounded in the AI's flaws or failure to balance different perspectives, right? So again, we have tried out this pedagogical design. This is how it looks like, in a more formal way. So you have your chatbot interaction, you have some pre-reflection, you have your human-human interaction, and then you have a post-reflection. So this also gives you a lot of formative assessment points for seeing how students' stances evolve over this course of learning. So what did we find? We found that actually more than 60% of the participant interactions in the initial chatbot interaction were actually coded with very high levels of critical thinking. So a low level would be something like accepting AI suggestions and taking it at face value. A high level would be actually questioning, bringing your own contributions to the AI. So this was coded by 2 independent traders. And for all our participants, more than 60% of the conversation turns were coded with levels, the highest levels of critical thinking, right? Again, it's the nature of the activity, right? Where you have to defend a biased perspective, which makes you go beyond just accepting, because it creates dissonance, right, with your own perspective. And then what we also found through thematic analysis is that interacting with the AI helped to nuance participants' views, right? So initially, views were quite balanced, but then towards the end, everybody had a more criteria-driven stance on when we should adopt AI for education, right? So the pre and post reflection, we compare the pre and post reflection to see how these stances had changed. And that's again a good data point to assess learning formatively. So in this case, the flaw, which is the biases of AI, and we're actually trying to fuel the biases of AI, but really prompting it to be even more biased. Actually, that's not a bug. That's a feature of the learning design, which creates this kind of learning opportunity for students. So what's the takeaway from this strand on learning with, or this example of learning with AI ed? Don't give learners AI access to find answers, but use the AI's inherent flaws. For example, their tendency to be biased. Or you can think of their tendency to hallucinate. Actually, those are very great instruction opportunities. Use that to our instructional advantage as we design new learning materials, right? In this case, we use those biases to prime a debate or start a conflict, right? And that's what good collaborative learning is. Good collaborative learning is not putting people together and the dominant one speaking up and everybody reaching premature consensus. Good collaborative learning is when people argue, right, about their own viewpoints and don't necessarily come to a consensus. That's not always good, right? So in this case, the human-AI interaction, this biased human-AI interaction actually creates a space for that argumentation to happen, right? All right, so let me share some of our work on this final strand of preparing for AI for education as we wrap up. So as students interact more and more with these AI systems, the fundamental question that we need to ask ourselves is, what properties should these AI systems have in the future, right, to trigger responsible self-directed learning? Now everybody talks about it, right? But are we actually working on building these kinds of systems to trigger these kinds of self-directed learning activities? I'm going to show you one such example. So one prototype that we have been testing is the design of affect-sensitive or emotion-sensitive conversational agents that students work with during an ill-structured problem-solving activity. And the agent can adaptively respond to how students are progressing through the problem and their emotions inferred in real time. In our case, the domain is data science. Now, we have deliberately designed this agent to reframe emotions as informative growth signals and preserve the struggle in the learning process. Now, these are both fundamental ideas in the learning sciences, but actually they are not currently enabled by the generation, like the generative AI systems that we have today. In our case, if you look at the help level map, the underlying learning sciences idea is that of productive failure. That helps us to design ways in which we preserve students' agency before we offer elaborated help. So actually, we look at the number of errors students make, the time that they take between different errors, and the semantic content of these errors, and use that to decide if we should offer detailed feedback or less detailed feedback. In most cases, our threshold is actually very high. So in very few cases, or very rare cases, would the agent actually give out the code, right? And we have programmed it to be like that in a way. On the other hand, if you look at the emotion response pipeline, which is the bottom sort of part of the figure, we think of emotion regulation not just as suppressing the negative emotions, but actually encouraging students to view all emotions as data points for growth. Now that's again a little bit of a difference in how we conceptualize what emotions mean for learning. So I'm going to show you some example responses from our conversational agent that will illustrate how it is actually very contextually sensitive to cognition and affect. And of course, we have not pre-programmed these responses. So this is one for boredom, for instance. And I'll just give you a few seconds to read through it. This is one for confusion, for example. Then there's awe, which students experience during the process of problem solving. There are things like disappointment, right? Just have a read yourself. And then there's tiredness as well. I've just picked out 5, right, which were inferred by our system. And in each case, what you see is that we don't offer generic advice like take a break, breathe. I mean, those are fine, right? But they're not matched to the content that students are trying to learn. So actually, we actually refrain from giving those kinds of advice during the process of problem solving. So you will see that each emotional response is actually tied to the content that students are actually working on, right? And I think that's the power of systems like these. I think generic advice, probably students won't take it seriously also. So well, what we found in a pilot study with our NTU students, a study design that looked something like this, where everybody interacted in a learning environment where this agent was integrated. So they did problem solving on an open-ended task. And then they looked at a video lecture in a way, or an interactive lecture. And then we had pre-test, post-test, and perception surveys. So I think one result that I would like to highlight here is that we found huge learning gains from pre-test to post-test. You know, with a system like this that responded to students' cognition and affect in a contextually sensitive way. And these effects are almost 2.4 times the effects of, you know, using computer-based scaffolding systems in problem-based learning based on prior meta-analytic work, right? So these are like huge, huge effects. Now, of course, we need to replicate it. We need to do it with a bigger sample, but initial results are not bad. So what's the takeaway from a teaching standpoint? From a teaching standpoint, preparing for AI-augmented self-directed learning entails developing dialogic systems like these that reframe emotions as informative growth signals and preserve struggle during the process of learning, right? And one has to deliberately design for it, right? And effective human-AI pedagogical partnerships must be contextually sensitive to cognition and affect. Okay, so I've spoken enough. Let me try to consolidate. So in summary, I've attempted to show you 3 different lenses that one can adopt when teaching AI for education. So one goal worth pursuing in this space is fostering AI readiness by teaching about AI, teaching with AI, and preparing for AI, right? And we expect this to increase students' capacity to think critically, right? And we also hope to reduce or mitigate the perception of AI threats because students are aware of what works, what fails in these AI systems. Now, this kind of a proactive teaching stance has shown encouraging improvements in teachers' preparedness to describe how AI works, how teachers can integrate AI in their teaching and learning, and to build new applications with AI tools. And I'm showing you results from various runs of an in-service professional development workshop that I've been running here at NIE for about 1.5 years. Right? And again, you see that if we deliberately think of pedagogies that are constructivist in a way, right? That preserve struggle, that don't dismiss emotions, that don't discredit emotional experiences, that can have some benefits in terms of improving readiness levels in a way. I think thank you very much for listening. Do encourage, your contacts to come and experience our courses, AI courses here at NIE. I mean, there's an exciting buffet. I couldn't list everything, because of space. But here are some courses that I've started or I'm involved in, right? Thank you. Open for questions. Do we have a space? Okay. Is everything clear or nothing is clear? It could be either way. Feel free to ask any question. Yes?
I don't know who the school leaders are. Are they the children who are the leading children, or are they the principals? Who are school leaders?
So these are, so there's a program that we have called the MLS program, which is for middle school leaders who
For
are,
adults.
yes, adult
I don't know that,
educators.
you see, because you're using terms I'm not familiar with.
Yes, so we have teachers, we have school leaders who are middle managers in schools, who have also been teachers previously, and then we have tertiary education students here at NTU. So actually we have looked at all.
So in the results which show different results, with the leaders eventually having learned more, although they self-assessed as worse,
Hmm.
is my understanding.
Yes.
Were they involved with the AI in a different way, or are you saying that as a group they behaved differently? And why was there a difference?
The activity and the pedagogical sequence was exactly the same. It was two different courses, but the way the activity was structured was exactly the same. So they were given some shared vocabulary about the terms of a neural network, and then we asked them, everybody, to then sort of work with the simulation and try to construct different kinds of networks. And then we did a perception survey and pre and post test and things like that. So the protocol was exactly the same. I think one reason for the difference could also be like just how teachers or school leaders would use these kind of ideas when they talk about AI. So I think for school leaders, probably it's a. So my sense is that they didn't take it very seriously while they were trying to work on it because they didn't see the relevance of that. Compared to teachers who can directly use something like this when they teach AI, on their own. So I think that can explain that initial difference in perceptions of usability, perceptions of learning effectiveness. But actually, if you don't take the learning experience seriously, that can still lead to higher learning because then you have to spend more effort to figure and try and understand like why things are working the way they are working. So the pre-post test questions actually targeted only the conceptual understanding of neural networks, not like factual kind of questions. So then that means that they had to really think through what they did, and it was a more effortful experience for them. We don't have measures of mental effort, but that's a conjecture that can be tested. Yes?
Actually, the school leaders perform better it could be because they are really selected, they have proven themselves. So the second part about them getting better results, they are proven, they are selected because they have really proven performance.
Well, that's partly behind my question.
So they can think better. So when you ask them the questions, of course, they will give you a better answers. So to get better results is logical.
So you can use this to screen for people you should promote to leadership.
Okay, that is not the intention at all. That would be, yes. That could be one reason. But I think in this case, the pretest scores were not that high. So one can assume that both the cohorts actually did not have a lot of prior experience, and especially with respect to the inner workings of a neural network. They probably knew something about, okay, neural networks has something to do with the brain, but actually they did not know how exactly these networks work. What are the inner underpinnings of a network? So there is that room for improvement in a way.
Are they aware they are being compared?
No. So this was actually done in two different classes, and this is just a comparative representation. But the goal of the study was not to necessarily compare the two initially. It was just to see or get some pilot data for how people are using the simulation. Right? So something that we have not looked at yet is the logs of the simulation, which tells us exactly where they clicked, how they constructed the network, how many times did they iterate, things like that. I think that kind of data is very useful. These simulations have those logs. We just haven't looked at it yet. So that can tell us more about the process, the learning process, not so much the outcome only, which at this point, yeah, there could be some alternative explanations as well, as you pointed out. Okay, that final question.
Yeah, thanks for your session just now. Just curious. I think in the second point you talked about learning with AI. And you mentioned that over 60% of participants showed critical engagement with the
Yes.
AI. So I'm just curious to know how exactly you operationalized and coded for
Okay, so we had a very simple coding scheme with 4 levels, 0, 1, 2, 3. So 0 is you take the suggestions of AI at face value. So essentially very, very brief responses, right? And then 1, 2, 3 are increasing levels of co-working with AI in a way. So 3, for example, would be questioning the AI, adding in more information, adding in new information to the chat or the conversation, things like that. So I can just like share with you the coding scheme, right? And we achieved like good reliability when 2 coders coded it. So it's simple enough that one can use it for any conversation.
So it's through the qualitative sort of like dialogue that they had with the AI chat.
Yes, so we actually collected their chats as well. And then we looked at it turn by turn. Yeah.
Thank you.
All right, thank you.